So good afternoon, everyone. On behalf of Current, it is my pleasure to welcome you to today's webinar on the NOVA principle, or as we like to call it, the supernova principle. So in today's webinar, we're going to be presenting many different use cases, which together will give a practical guide to what energy efficiency means in the context of the electricity grid. So for today's agenda, we will start with a presentation by Frederic Vassort, who will present a dynamic line rating use case. Then we'll have Peter Hughes presenting on advanced conductors. Next, we will have Hedd Roberts presenting a smart valve use case from the UK, and Lars presenting a grid booster use case. Finally, we'll have Patricia Labra, who will present on behalf of ENSOE. So my name is Leila Sawyer, and I'll be moderating the webinar for today. So as a reminder to everyone, this webinar will be recorded and a PDF of the slides will be made available on our website. And if you have any questions for our speakers, feel free to ask them in the Q&A session. But before I hand over to today's speakers, I would like to first give a brief introduction of Current and why the NOVA principle and energy efficiency is such an important and timely topic. So first of all, Current is the voice of innovative grid technology companies in Europe. Next slide, please. And our members work on solutions that can increase the transfer capacity of existing lines, as well as increase the efficiency of new lines. And this can be done through dynamic line rating, modular SSSCs, superconductor cables, storage solutions, etc. Next slide, please. Many studies have already been done on the benefits these technologies can bring to the energy system. In one study by Concentric, for example, it was measured that, previous slide. Previous. Oh, sorry, the slides seem to have gotten out of order. But why this is important now, particularly now, I don't need to tell anyone here facing in Europe, the war in Ukraine, the high gas prices, the planned phase out of Russian fossil fuels, and the risk of being cut off altogether, as well as many other challenges. So on December 1st, ENSOE presented their winter outlook for this study and for this winter until March. And although there are many variables, the conclusion is that we are in a more critical situation than in previous winters. So system stress identified in Ireland, France, southern Sweden, Finland, Malta, and Cyprus. And although weather conditions might be favorable this winter, we are also facing uncertainties around nuclear availability in France, Sweden, and Finland, as well as coal shortages in Germany and Poland. Yeah. At the same time, we have been hearing for a while that the real challenge is going to be next winter. And the IEA has yesterday released a report on the remaining demand supply gap for winter 23-24. Despite the actions that have already been taken and how we might address these, and of course, renewables, efficiency, and electrification are an important part of that solution. This, of course, means that we need to plan ahead for this on our electricity grids. And as the IEA has put it in their report, we need to ensure sufficient gas capacity to allow renewable consumption to displace gas consumption. And this is where the NOVA principle comes in. So the NOVA principle is a German acronym, which means optimization ahead of reinforcement, ahead of building new lines. And this is, of course, important in general because using our infrastructure efficiency means saving costs for everyone. But it is particularly important now when we are trying to move very quickly to continue to ensure security of supply for the winters to come. And of course, in some cases, building new lines is the best solution, but this is why it is particularly important that we are transparent in considering which solutions are best, and that we consider all options that could solve a certain problem. Next slide. So this is where our innovative grid technologies come in, the different solutions for the problem. Yeah, many reports have been written on this already, on the benefits and how they can support the electricity system to integrate renewables faster and plan for an electricity grid that can support a fully decarbonized economy in 2050. So everything has been said already, but we see that these technologies are still underutilized and often overlooked, which is why I'm very happy our speakers can share their insights on this today. So without further ado, it is my pleasure to announce Frederic Vassort, CEO of Empassimon, who will present a dynamic line rating use case. So over to you, Frederic.
Good afternoon, everyone. My name is Frederic Vassort. I'm the CEO of Empassimon. Next, please. I'm going to talk today about the advantages of using dynamic line rating, briefly cover what dynamic line rating is and how it has been used already through a couple of use cases. Next. So dynamic line rating is a way to optimize transmission lines, overhead transmission lines, by taking advantage of the fact that lines are cooled down by prevailing weather and wind. So when the weather is cold, like in most of Europe today, or when the wind is blowing, the lines are cooled down and therefore their transmission capacity increases. And we have done at Empassimon, we've done hundreds of deployments the world over. And what we note is, and I'm just trying to mention some, some orders of magnitudes here. What we see routinely is that whenever lines are equipped with dynamic line rating, the capacity gains typically range in 10 to 20%, available 90% of the time. Of course, there are also some instances where the capacity can be much higher. We quite often see capacity doubling when the wind blows and when the weather is cold, but that's not really the point. And the point is to make sure that that capacity is available most of the time, to be able to forecast it and to be able to make sure that under no circumstance do we put the grid at risk, which is why monitoring is important. Next. Yeah. So here is an example of what dynamic line rating delivers. You can see on the chart on the left side of this page, the red horizontal line is a nominal rating of a line. In this case, it's a 380 kV line in Belgium. It's an interconnector, which is normally rated at around 2,800 amps. By using dynamic line rating in real time, that's the green curve, you can see that and this is a long period of time, right? We're talking about 2,000 hours here. You can see that the rating increases routinely above 4,000, and quite often, or most of the time, in fact, is above 3,000 amps. So that's for real time. Now, the real value of dynamic line rating is to be able to forecast it so that free capacity can be made available to the day-ahead market and can really be used in particular for interconnectors. And that's the orange curve on this same graph, where you see that, of course, the forecast is lower than real time by design, and that's what we strive to do in our algorithm, is never to allow the grid to be put at risk, and therefore the real time should always be higher than the announced forecast. But still, the forecast mode delivers, in this example, more than 1,000 amps extra capacity most of the time. On the right side of this page is just a different way to plot the data. You can see that the mean value in this example is around 130 and 140% above the nominal rating of the line, in that indeed 90% of the time there's somewhere between 15 to 20% of extra capacity available. What is really important, and I want to stress that, is that to be able to take advantage of that, you need to monitor the line properly with sensors. That's what we do at Ampersimmon, to make sure that you do capture properly the critical parameters of these lines, and in particular that the wind speed is properly measured, particularly at low wind speeds. Next. So what does it deliver? Well, of course, it reduces congestion costs. It allows operators to avoid counter trading, to avoid curtailment, to avoid load shedding. You know, all these kind of very expensive measures. And by simply using the existing infrastructure closer to its true limits, but still in a completely safe way. And in this example, we'll come to it in a minute, we see that, you know, we can save up to, or the operator can save up to €500,000 a day. So needless to say that the payback on these investments is almost instantaneous. Of course, it also, by the same token, increase the in-feed of the available generation. We'll come back in a minute to the specific case of wind renewables, which have a nice correlation with DLR. It can increase cross-border exchanges, which is it's a key factor this winter. It will be probably even more important next winter. DLR is a great way for TSOs to meet the 70% target set by ESSER, which they will have to comply with very shortly, simply by allowing the lines to come closer to their real true capacity. Next. I mentioned already, reducing the need for remedial actions, changing PST tappings, curtailment. All of these is extremely expensive. It can also be used. That's an added advantage. Whenever a line is down, you can use DLR on nearby lines to divert the flow that would otherwise have to be redirected on more through more expensive means. I talked about renewables integration. That's a very important topic because, as I mentioned at the beginning, most of the value of the DLR is due to wind cooling the lines, and it's quite natural to understand that if the wind that blows on the lines increases their capacity, the same wind would also blow on windmills, on wind farms, and therefore there's a natural correlation between hosting capacity of wind farms and DLR. And we have numerous examples that have shown that if DLR is used on lines adjacent or close enough to wind parks, we can increase the capacity, the hosting capacity of those pockets of grids by as much as 50%, or reduce the curtailment of existing wind farms by as much as 15%. So I mentioned several times that it's really important to do all of that in a very cautious way, and the fact that dynamic line rating is by design a monitoring technology. So there are sensors that are constantly measuring the key parameters of overhead lines. That in fact it actually improves the controllability of the grid. It reduces the risk because it gives real-time visibility of all key parameters that typically limit the capacity of a line. And we have seen in the summer, in hot days, we have seen examples where the rating is actually lower than the nominal rating. Therefore, even though you don't gain capacity in these examples, but you actually gain safety, which is equally important. Last but not least, of course, if you deploy DLR on lines, it allows operators and TSOs to defer grid investments. We're certainly not advocating that DLR can replace lines. That's not the point, but it can certainly allow TSOs to manage their CapEx and their investments in a more optimal way, because if DLR is deployed on certain lines, and that's what our customers do routinely, they can defer investments which to deploy this capital on more urgent projects. Next. So here's a typical example. That's an example we of a project we deployed at Elia in Belgium. Belgium is crisscrossed by lots of loop flows coming from the north of Europe to be dispatched to the south of Europe and for north, south, and east, west. And it is on top of that already hosting a lot of renewables, particularly wind farms on the North Sea, which is on top of this of the map here. So I wanted to talk about this specific example. It's a 380 kV line that crosses the country from Holland, Netherlands to France, and on top of that also sees very large infeed from a 900 megawatt wind park located in the North Sea. So faced with that, confronted with that, Elia, obviously they are going to reinforce this corridor. That's going to take several years. It's in progress, but in the meantime, they deployed DLR, which did two things. It improved interconnections with neighbors, in this case France and the Netherlands, and it also allowed them to connect the wind park that was being built in the North Sea without having to do grid reinforcements, at least during a few years. They were able to quantify the savings obtained by this project, and simply by avoiding international redispatch, they saved €500,000 in a day. So needless to say that the payback of such a project is quasi instantaneous. But even more importantly than the financial aspects, the operational aspect of being able to find a solution to accommodate these extra flows without having to wait months and months and months for line reinforcement or years for a new line is really where the value of such technology comes. Next. So that concludes my presentation, this short example of a use case of DLR, and I hope I'll have an opportunity to answer your questions later on during this session. Thank you.
Thank you very much for that, Frederic. I think all of us would be happy to save 500 billion in a single day. So definitely something for policymakers to consider. My question, maybe just a quick question to you, Frederic. Dynamic line rating, is this something that is already being widely done, or how is it there? I assume there's much more potential for this still.
Yeah, it was 500,000 euros, not 500 billion.
Oh, sorry, my mistake.
In a day, but if you can multiply that by the full year, it's still a large amount. We're starting to see large-scale DLR deployments. There were a few pioneers in Europe. Elia was one of them. But now, thanks to favorable regulatory changes, we wish they were faster, but they're starting to happen. We're seeing DLR being more widely deployed now. I think it's fair to say that now most European TSOs are familiar with the technology in one form or some form of shape. The US are also embarking on this very aggressively, also favored by a more favorable regulatory environment. So now we're seeing more and more grid operators deploying DLR on a large number of lines, at least on all their congestion lines. We're also seeing DSOs actually deploying that. But there's still, it's just the beginning, I believe, of this market adoption. But I think it's fair to say that finally the speed of adoption is picking up.
Thank you very much for that, Frederic. Yes, 500,000 is different than 500 billion. But okay, you heard it here. We are at the beginning of this. So thanks, Frederic. And now it is my pleasure to present Peter Hughes, European Vice President at CTC Global, who will be talking about advanced conductors. So thank you, Peter. The floor is yours.
Yes, thank you, Leila. I think at 500,000 a day, I'm in the wrong business, but nevertheless, I'll continue. So in this section, we'd like to mainly address the reinforcement of the overhead line, focusing on advanced conductors and the role they play in the energy transition, and we'll also touch on TYNDP. You have the next slide or the first slide, please, Jürgen, and if you move on to the next one, please. So just to recap, this is the NOVA principle, which we took from the Bundesnetzagentur. So it's Netzoptimierung vor Verstärkung vor Ausbau. And Simon eloquently delivered the reasons why DNR fits so neatly in this optimization part. In this part, I'm going to focus mainly on the reinforcement of existing routes. That's the V of NOVA, and would also touch on new lines, the A of NOVA. I dropped down the HTLS, as you can see here, and high temperature, low sag, better known as HTLS conductors, play a major role in the NOVA principle. Because HTLS conductors directly replace older technologies with more capacity, they provide an easy solution to reinforcement requirements when reinforcement is necessary, of course, as Frederic was saying earlier. So, but what do we mean by HTLS? So the next few slides, I'm just going to explore a little bit the development of conductors over the years and this role that they play. And then I'll move on to a use case also with Elia in Belgium. Could I have the next slide, please? So this is a little graphic of the timeline of overhead line conductor evolution. And note the timeline here. So most HTLS conductors, as you can see from this slide, are essentially high temperature variants of the original ACSR design, which goes back to the 1920s. And they all, to a greater or lesser extent, suffer from either aluminium stability issues due to temperature, memory sag as they're heated up, or high resistive losses, and also corona noise at elevated voltages. And as we're talking primarily about transmission networks in this seminar, that's particularly important. So in this slide, you can see I've put just click it, please, Jürgen. Thank you. Inside this green box reflects the main topic of what I'm going to talk about today and its application. The early 2000s saw the development of carbon fiber composite and metal matrix core conductors. Replacing steel with carbon fiber composite and metal matrix yield massive benefits, not only in stag stability, but also transmission efficiency. They're generally categorized as advanced conductors in the industry. And CTC Global, my company, was an early pioneer in this with its ACCC or ACCC conductor. And just to give you some background on track record, the first ACCC installations took place in 2005. And to date, we've installed around about 12,000 kilometers in Europe. More recently, definitely because of TYNDP and the Green Deal, but it's been gradually accelerating year on year. So in this category, advanced conductors, why would they be chosen over their cheaper steel-based alternatives? And the clue is in this classification, which we put here, high capacity, low sag. And in the next slide, I'm going to talk a little bit about the technology and how it actually works. Could you move it on, please, Jürgen? Thank you. So in this slide, we compare advanced conductors with their steel core counterparts in a bit more detail. And if you can have a look at the picture, please, you'll see a significant difference between the conductor on the left and the one on the right. So in terms of performance, we must consider the conductor on the left as a system. And this means that the steel core and alloy conductor strands all act together to provide the conductor with its inherent strength. For the conductor on the right, that's not the case. It's only the composite core that finally delivers the mechanical properties above a given temperature. This permits the use of pure aluminium as the conductor material because it doesn't require mechanical properties, and pure aluminium compared to an alloy has about 10% less inherent resistance than its alloy equivalent. As the composite core is much lighter than its steel core equivalent, we get over 20% extra conductive material for a given diameter. And you can see that clearly in the picture. There's much more fill. So that's really the high capacity part of this technology. And by high capacity, we also mean lower resistive losses per kilometer, or lower to operating temperatures for the same current. And, you know, it's better to have more capacity at the same or lower temperature, means less generation. The Rocky Mountain Institute did a study on this a few years ago. I can take it offline later, called Negawatt is better than a megawatt. And some of the calculations that we've done for both National Grid and Tenet on this even shocked us at the amount of annual generation savings, CO2 reductions, because they're both still using fossil fuels to a greater or lesser extent, and also knocking out potentially turbines, wind turbines. Anyway, moving on. Low sag shared with classic HTLS conductors. Steel expands with heat, as we all know, and permanently stretches over time. Composites, however, are lighter, stronger, and stiffer, and most significantly, exhibit almost no thermal elongation. In technical terms, no coefficient, very low coefficient of thermal expansion. And that's the low sag part of this. So these two factors, increased capacity at lower operating temperatures and a largely fixed sag profile throughout the life of the conductor, deliver lowest lifetime cost for reinforcement projects, easier permitting, and just as significantly, network future-proofing. So in the next couple of slides, I'd like to introduce a TSO use case, in this case, the ELIA MMVE project. Jürgen, if you could move the slide on. Thank you. So this is a route, ELIA Massenhoven Meerhout to Van Eyck, or MMVE. I apologize to the Dutch speakers for my very poor pronunciation on this call, but keep trying. So ELIA, through its Act Now sustainability program, is at the forefront of the energy transition in Europe, and also a highly innovative TSO, as Frederic was saying earlier. ELIA also, as Frederic was saying, needs to be deeply interconnected with its neighbours in the coming decades to meet its EU TYNDP interconnector obligations for this pan-European network. I believe you'll hear more about TYNDP itself later during Patricia Labra's part of this seminar. Because of the complexity of this 92-kilometre route and the time constraints involved, building a new connection, in other words, a new line, was not an option. So it presented an ideal candidate for reinforcement with advanced conductors, delivering double the capacity of what was already on there, the legacy 620 AAAC conductor. Frankly, I'd love to go into more detail on this project, but time won't allow it on this seminar. But I have put a link at the bottom of that slide, which should work on the PDF version. And so please check it out, and you'll see more about the route, the challenges, and the solutions that were adopted on it. Could I have the next slide, please, Jürgen? So here's a bit of eye candy. We included a couple of illustrations on some of the innovative techniques that ELIA deployed on this project. The illustration on the left hardly needs a description, but it shows a helicopter asset being used to install a pilot line prior to project start. Another innovation implemented on the right Elia partnered with CTC Global for an innovative core integrity inspection system, which was originally developed by CTC. This system attaches to the composite core after installation, and it helps ensure the conductor has been properly installed by the contractor. So could you move on to the next slide, please, Jürgen? So finally, really, why would Elia install a conductor technology that I've already said is significantly more expensive per meter than a traditional HTLS conductor? And here are what I think the main reasons why, and I'm sure that somebody from Elia is on the call and will be able to expand on this. High capacity. Utilities like Elia can easily reinforce their network with a minimum of civil work or additional permitting. Low sag. I described earlier how this works with an advanced conductor. So a guaranteed catenary or sag profile ensures existing rights of way are maintained and often case narrowed. We see that more and more with wildfire considerations, particularly in the US. Efficiency gains. As previously described, greater conductor fill and a more conductive material yield up to 40% more baseline capacity from the get-go. And this ties in with future-proofing. With double the transmission capacity, advanced conductors like ACCC allow TSOs to cater for future demands. And this is particularly important as modern grids need to be ready for previously unseen, unplanned renewable generation. And last, but by no means least, advanced conductors like ACCC rarely need any major civil work, such as tower and foundation strengthening or tower jacking, to deliver much more capacity within a given pathway. Add the much easier permitting and network reinforcement on existing routes with advanced conductors to that, and they are a very highly cost-effective solution. I must stress very often, as we hear from utilities after installation, at lowest project cost. You'll note that I haven't discussed new lines on this, again, bearing in mind the limitations of time. But our experience has shown that advanced conductors like ACCC can also significantly reduce overall project costs. And how do they actually deliver this? Well, the stronger core that I was describing earlier optimizes the number of towers on a given route. So we can reduce the number of towers compared to a standard conductor or even a standard HTLS conductor. And each tower is never less than 200,000 at best in Northern Europe, plus all of the permitting, as well as reducing the number of conductors in a given bundle configuration. So I've put finally the conclusion here. Advanced conductors have, I think, greatly enhanced the utilities toolbox for cost-effectively and reliably ensuring that the European network is fit for 55. And I think that concludes my slides. Just move on to the next one, please, Jürgen. Thank you very much. Thank you for your attention. You'll see my contact details in that last slide.
So thank you very much for that, Peter. I think a very clear overview of the different benefits that advanced conductors can bring. And of course, going forward, it's so important to think of future-proofing the electricity lines, also when building new lines and reinforcing them. And on behalf of Dutch speakers, I forgive your pronunciation. There is a question in the Q&A for you, which is about the increase in capacity, but maybe I leave you to answer it in the Q&A section. Then I would now like to move on to our next speaker, Hedd Roberts, General Manager Europe at SmartWires. Hedd, over to you.
Thanks so much, Leila, and good afternoon, everybody. If we could have the next slide, Jürgen, please. So I'm going to talk a little bit about a case study in the UK on National Grid's network for SmartWires devices this afternoon. So if we could go to the next one, Jürgen, please. A quick introduction to SmartWires. I won't say very much here. It's a US company. Our main office, tech hub and HQ is in North Carolina in the USA. But we also have offices in Ireland, Colombia, and Australia, and a global workforce, essentially, people based everywhere. And the main role of SmartWires is advanced modular power flow control. And that's the example in the UK that I'm going to talk through. If we could go to the next one, Jürgen, please. I think before talking about a use case in the UK or in GB, it's probably worth just a little bit of context and scene setting on the arrangements in GB for increases in transmission capacity and transmission boundary capacity in particular. So in the UK, there is an independent system operator and a legally separate transmission owner. And the electricity system operator runs an annual process called a network options assessment to assess the proposals that are made by transmission owners to increase boundary capacity on main transmission system boundaries. And that assessment, as I say, it's run annually. It does somewhat ensure that the uncertainty of future need is taken into account because multiple future scenarios are considered. But ultimately, the transmission owner proposals that get the green light are those that minimize regret when across those scenarios, when both investment financing costs and congestion costs are considered. It's also worth bearing in mind that the transmission owner price control, so its agreements with the regulator, Ofgem, includes unit cost allowances for boundary capacity that are set in advance based on the available technology. So price controls run now every 5 years. In coming up with our price control agreements, the unit cost allowances for increases in capacity across boundaries are set in advance. That means that if the transmission owner can find a different way of increasing boundary capacity during the price control period that is less expensive, then the savings are essentially shared between the transmission owner and consumers. And I think I'm going into that in a bit of detail because I think it is important when we're to think about that context and those arrangements when we think about how grid enhancing technologies are rolled out. If we go to the next slide, please, Jürgen. So the main modular power flow control device that SmartWires is responsible for is a static synchronous series compensator. As I say, it's modular. So that's essentially a power electronics device which injects a controllable voltage, either leading or lagging, such that this gives control over the effective impedance of the circuits that the smart valves are connected into. I won't go through this in a lot of detail, but I think that the main thing to bring out here is just the flexibility of these devices. So they take their power from the circuits they're connected to. There's no auxiliary power supply or anything like that. And the civil works, etc., to accommodate them are relatively minimal. So they can be deployed, redeployed, extended quickly and easily. Which is really important when we think about the uncertainty that exists in transmission networks today. If we go to the next slide, please, Jürgen, we'll talk a little bit more about the case study in the UK. So the problem that we're trying to solve here is a lack of transmission capacity, and that's caused by increased amount of renewable generation in Scotland in the north, causing increased power flows north to south towards the main demand centre of London in the south. So I guess, a lot of commonality with a number of the use cases that we're talking about this afternoon. In particular, that power flow is constrained by a number of bottleneck boundaries, both between Scotland and England and in Northern England. And you can see those boundaries highlighted as B6, B7, and B7A on the map of the Great Britain network on the right-hand side. There are some major reinforcements planned to increase the capacity of those boundaries, including offshore HVDC cables, HVDC links. But of course, projects like that take a long time to come to fruition. And the other thing to bear in mind is that if we were to sum all of the thermal capacities of all the circuits that cross those boundaries, that sum is much higher than the declared capacity of those boundaries as a result of circuit sharing. So if we go to the next slide, please, Jürgen. So this is the solution. It's essentially to deploy smart valves at substations in the north of England such that that circuit sharing is improved, and as a result, boundary capacity is increased. So you can see that the stage 1 deployment here was 48 smart valves across 3 substations in northern England, Harker, Penwortham and Saltholme. And at those substations, those smart valves were connected into 5 separate circuits. So that initial deployment increased the boundary capacity of B6 by 500 megawatts, B7 by 900, B7A by 500. And the headline impact there is a significant saving for GB consumers, so 387 million. That was achieved very quickly. And as I mentioned before, the key thing here is the flexibility, the expandability and redeployability of the devices. So much so, in fact, that National Grid built on the success of those stage 1 installations with extensions to the deployments at both Harker and Penwortham. Another 18 smart valve devices were deployed, and that further increased boundary capacities to, as you can see on the slide there, another 400 megawatts on B6, 500 on B7, and 200 on B7A. So a significant increase again. If we just go to the next slide, Jürgen. So this is a representation of one of those sites, Harker, where you can see we've got 5 devices per phase in the Harker to Forestone circuit, 2 devices per phase in the Harker to Stella West circuit. That was the original stage 1 installation. And then if we just go to the next slide, you can see that, that the amount of devices was doubled actually. So from 5 to 10 in the Harker Forestone circuit and 2 to 4 in the Harker Stella West circuit. That was the extension project. And the important thing here is that by double stacking the devices in this way, we were able to achieve that extension with no increase to the footprint associated with the initial deployment. So onto my final slide, Jürgen, please. Yeah, that's me. If anybody has any questions or otherwise after, then please don't hesitate to get in touch. Just to summarize, the significant need for significant increases in power flow, and they were achieved very quickly by increasing the improving the sharing on transmission system boundaries using smart valve devices. Thanks, Leila.
Thanks, Hedd. So just a question from my side. So projects, so this can already make a big difference for next winter if we make plans for this now.
Yeah, it is possible. I mean, I think that those extension projects, so when we went from stage 1 to stage 2, they were achieved in about 12 months. So it can be really, really quick. Of course, as with everyone else, I'm sure we're not without issues in supply chain at the moment. So you know that would always be the subject of more detailed analysis. But you know we've proved it in the past with the UK need case. So those sort of timelines are certainly possible.
Thank you very much, Hedd. And now I would like to give the floor to Can you hear me? Okay, I don't know why. I had a gremlin in the computer trying to mute me. I would now like to give the floor to Lars Stephan, Policy and Market Development Manager at Fluence. The floor is yours, Lars.
Thanks, Laila. Yeah, thank you. First of all, thanks for inviting me to talk today at the webinar, and also really thankful for what the three speakers just had to say, because I think for me, who's also still new in that segment, it's quite exciting to see how smart technologies can make such a huge difference, increasing the utilization of existing transmission lines. And this is exactly what I want to talk about as well, based on the Grid Booster project in Germany, where the same thing can be done with energy storage. But of course, also thanks to everyone who is dialed in today, listening to us, and for the great engagement that we have via this discussion chat already. And if you have any questions, please post it in there. So quickly about myself, my name is Lars. I'm global co-lead of our TSO initiative at Fluence. Fluence is a global leading product company for energy storage solutions, services, and digital applications. And we use energy storage or storage as transmission assets, which is like a new kind of technology class, both for TSOs, but also in the storage space, to increase utilization of transmission assets, transmission lines, and also provide advanced service operation capability to system operators. Maybe if we jump to the next slide. For Fluence, we have deployed or contracted more than 5 GW of storage globally, and around 500 MW of that is in the TSO space, so specifically to TSO customers, mainly in Europe. On the one side, we're having a 200 MW portfolio in Lithuania, where the asset is more about system stability and helping the country to disconnect from the Russian grid and synchronize with the continental European grid. And now this announcement about a 250 MW storage asset, a grid booster asset that we're building in the German transmission line for the German system operator Transnet BW. If you jump to the next slide, to provide some context to the project and to the problems that we face in Germany, it's actually very similar to what we just heard from Hedd about the UK context. So in Germany, we have a lot of conventional generators, traditionally in the south, where the load centers are, which are being disconnected because they coal their nuclear plants. And at the same time, we're integrating a lot of wind resources, offshore wind resources in the north of Germany. This means now we change the paradigm of German grid, where we have to transport a lot of energy from the north of Germany to the south of Germany. And this, of course, as the grid typically cannot adopt as quickly, comes with congestion within Germany. Last year, the congestion cost for not having the right grid for the generation load mix in Germany was about 2.3 billion euros last year. And we understand that this year, the cost of congestion of the German grid will be north of 10 billion euros. So this is 10 billion euros paid because we don't have the sufficient and right design of the transmission grid in Germany and have congestion in it. So that is obviously a huge problem. The grid operators are addressing it by building HVDC connection lines. Actually, there are multiple corridors being in planning and execution right now. But of course, building transmission lines 506 kilometers from north of Germany to the south of Germany takes a lot of time. This is why in the 2019 grid development plan, the German TSOs for the first time have proposed to build those called grid booster batteries into the German transmission grid as an asset that can be deployed quickly and increase the utilization of transmission lines. The assets were first introduced 2019. They were affirmed back then, at least 2 of those assets by the German regulator. They were reintroduced 2021. The grid development plan were reaffirmed, and now both assets are under procurement. So as I just mentioned, the Transnet BW asset, which will be one 250 MW battery, was awarded to Fluence at the end of September, and the other asset, which is 2 100 MW batteries, will be awarded towards the end of the year, beginning of next year. So what do those assets, what do those batteries in the grid actually do? Because if we think about energy storage, we often think about, of course, charging and discharging energy. And there are certain projects like that, like the Ringo project in France, for example, where storage does exactly that to overcome grid congestion. But these batteries here are used in a different way. I always like to say, if everything goes correctly over the 20-year lifetime of those batteries, they will not be used a single time, because they really act as a contingency reserve in the German grid. So grids, especially in Germany, but in many other countries, of course, around the world, are typically operated on an N-1 contingency requirement. That means we always keep spare capacity in our transmission grid in case we have a contingency event, like a fault at the substation, or like a problem with a line. One line goes out, we cannot use it anymore. The other lines that we have in a grid area can pick up the electricity flows that were previously on the line that now had a fault condition. So this means, in turn, that we always keep spare capacity on our lines. So we have lines which we're actually not utilizing because we're holding back capacity for security reasons. Using batteries within the transmission grid used as a transmission asset, we change this paradigm and we move this contingency element onto the battery. This means now we're utilizing the transmission line to its fullest capacity. And if a contingency event was to occur, those batteries, which are called grid boosters, will react within 150 milliseconds and start charging on the one side and discharging on the other side of those corridors. So reacting really, really quickly to contingency events in the grid, and thereby preventing us to keep transmission line capacity underutilized. So this is really the whole trick of it. What that means in turn is, of course, that we have existing transmission lines, we can increase utilization, which directly translates in less congestion, translates in less curtailment of renewable energy that happens in Germany on a large scale. Very interesting also to mention, we like to talk about a German concept because we have it in the German grid development plan, but we're seeing similar projects around the world. In Australia, the Waratah Big Battery had been awarded, which is a 700 megawatt asset, so really big. In Chile, and 2 500 megawatt assets are currently under development. They will be tendered soon. So this concept of using storage as transmission asset, not discharging energy, but acting as a fast backup solution, is something that we see more broadly around the world. We jump to the next slide. Quickly talking about what else batteries can do. It's actually quite interesting because batteries are an asset that can provide many different services. So from an application perspective, this grid booster functionality is also called SPPS, or providing an EPC signal, which is an emergency power contribution signal. But the Transnet asset, according to the grid development plan, will also provide reactive power control services at the location where it's placed in the grid, which will have a monetary value of 60 million euros over the 20-year asset lifetime. So that is quite interesting. Going forward, we see those assets being able to provide things like inertia, dynamic voltage control, power oscillation dampening. So a lot of things those assets can do. Many of those products don't exist yet today, but we know that as we move away from rotating masses, inertia from synchronous machines in the grid to an inverter-based power system, that we will need new ways to provide system inertia, system stability services, black start capability, for example. And these are things that those assets are already able to do. So that's quite exciting because we think once we have those assets, they can do other things as well without interfering with markets, which is very important from a regulatory, from an unbundling perspective, if we talk about battery or storage ownership by TSO. Maybe if we jump to the last slide, this is just maybe a little teaser, because a problem about the grid booster model in Germany is that the Germans like to speak German, and therefore mostly all documentation about the grid booster is in German. So we are actually in January launching 2 studies, actually written by Consentec, which also did already great work for Current, and really loved what they did with them. That's why we went to Consentec as well. And we'll launch 2 studies. One will explain into more detail how the operational functionality of grid boosters actually work and how it drives value in increasing grid utilization. And the second study will talk about functionality stacking onto those assets, which will also, I think, be interesting going forward as we think about energy storage as transmission asset, providing additional values and services to the grid as well. So we'll see this studies published in January, and that's the Grid Booster introduction. I'm looking forward to any questions the audience might have, or Laila might have.
No. Thanks. Thanks, Lars. Thanks for that presentation. Great that you also worked with Consentec. Also interesting to see that in other countries, you're also working in a lot of other countries outside of Europe. I know a lot of our members are also working in that. Do you find that it's going faster in those countries compared to in the EU context, or we can save it for the panel discussion as well, but if you have some initial thoughts.
I have an initial thought, and one of them is probably need in the system drives speed. You could probably say so. The asset in Australia, it was first thought of and then tendered in less than a year. So the system operator realized, wow, we have a big problem, which is in Australia caused by coal power plants exiting the market. And they had this emergency procurement and tendered the asset within a year. So building a 700 megawatt battery takes a bit of time, probably 1.5 years, but really fast. If you compare it to Germany, those assets were first introduced in the 2019 grid development plan. They're now being awarded 2022, and they will only become fully operational 2025. So that's still faster than building a huge HVDC line north to south, but things could be faster. So I think as we see more of those projects coming online, and I think the same is true with all the different technologies we heard about here today, as TSOs gather experience about it, I think they will be able to faster deploy those assets and use them to increase the utilization of the transmission lines, which is, I think, a good thing going forward. But maybe also then with our next speaker, Patricia, will hear more about it as well.
Thank you. Thank you very much. Thank you for the last use case presented today. And now I would like to give the floor to Patricia Labra, who is Head of Network Planning at Red Electrica, and is today speaking as convener of the TYNDP on behalf of ENSOE. Patricia, we have seen a lot of different use cases today, giving a more practical dimension to the NOVA principle. I give you the floor maybe to reflect on this, also how this fits in the TYNDP process. Yeah, over to you.
Okay, well, thank you, Laila. Thank you very much for the invitation to share with you the view of ENSOE, the Association of European Transmission System Operators. You can go to the next slide. You will probably know the 10-year network development plan. It is the European Electricity Infrastructure Development Plan, and here, as it says in the slide, yeah, it provides a pan-European vision of the future power system and investigates how power links and storage can be used to make the energy transition happen in a cost-effective and secure way. Well, if we go to the next slide, one of the main break of this plan is the identification of system needs exercise. Yeah? The objective of this study is to investigate where improving the electricity flow through Europe could be the most cost efficient from a pan-European perspective. The main findings here of this study is that there are opportunities for improving the power system all over Europe. Yeah, that addressing those system needs allow us to reduce the Europe dependence on gas-fired power generation. That's something that you, Laila, mentioned at the beginning, and it's very relevant for the next year. And also, of course, that coordinated planning will be needed across sectors in order to allow the integration with gas and many other sectors as well. In the next slide, in this figure, you can see the map of the 2040 needs. Yeah, here we can see around 88 gigas of additional cross-border capacity on top of the 2025 grid, and that's over 65 borders. Yeah. In addition, it has been also identified the need for 41 gigas of battery storage and even 3 gigas of CO2 free picking units. Yeah. In 2040, the highest needs for capacity increases are in all French borders, especially with the Iberian Peninsula, on UK continent borders, and to accommodate flows between southeastern and central Europe, from Turkey through the Balkan Peninsula, all the way to the Czech Republic. Yeah. In most of Western and Central Europe, these capacity increases are complemented by storage flexibility, with highest need in Spain with more than 10 gigas, Germany between 5 and 10 gigas, Italy, Portugal, Hungary, and to a much lower extent by peaking flexibility in Hungary and Poland and isolated areas such as Corsica or Malta. There are also a significant increase in needs after 2030 on Italian borders and borders between Scandinavian countries and mainland Europe. These values have been identified because the study showed an economic interest to solve them. If we go to the next slide, I will also like to mention that the goal of the needs study is not the solution, but where the needs are. For the solutions, the modelization only allows to include some solutions, but the way to interpret it, because as you saw, they were mainly as capacity increases, yeah. But the way to interpret these needs is that, well, reaching Europe's Green Deal objectives will require exploring all possible solutions to bridge the gap. Identified needs can be addressed in multiple ways. So that's included infrastructure solutions, new or upgraded transmission infrastructure, electricity storage, power to gas or hybrid infrastructure, and also non-wire or non-infrastructure solutions, such as some of the ones that we have been seen in the previous presentations, yeah, but also can come from the demand side response, from regulation, from market design, for sector integrations and operational measures. There are a lot of possibilities ahead, and all possible solutions should be considered by project promoters and policymakers when opportunities stand in through project. Yeah. Okay, and if we go to the next slide, we can see here the example of the last Spanish network development plan, where to solve identify need a step. Oh, sorry, I have lost the light. Okay, this is the example of the last Spanish network development plan that was published this year in the spring, where to solve identify need. There is a step-by-step process from least environmental and economic impact to solutions. They are assessed first. That means as a first step, operational measures in the control center, for instance, such as the automatic power reduction system that allows to eliminate more than 50% of the midterm system needs and allows higher res integration. But the next steps also include a better use of current infrastructure, such as devices to have dynamic capacity of power lines, devices as the ones presented by Frederic, or upgrade of existing capacity by making pylons higher, or tense the sag, or even using high capacity conductors that allow capacity increases up to 40% in the low sag ones, as we saw at the presentation of Peter. Yeah, also FACS, flexible AC transmission system, synchronous compensators as the one proposed by Hedd, or even batteries as full integrated network elements, as in the example of Lars, because you didn't mention the example of Spain, but it's also we have also one. It's not for res integration specifically, but it's for allow to increase the capacity in a link between the mainline system and the Balearic system. But it's also an example, and it has been included in the last National Development Plan. and only consider all these options, and only when no other alternative is feasible, new investments are considered as solutions to the needs. And this is a energy efficiency approach, and it's a common approach among every TSO to solve the needs. If we go to the next slide, with this in mind, ENTSO-E is calling for a clear, coherent regulatory frameworks that accelerate the development and deployment of innovative solutions. Yeah, a classic incentive regulation driver by cost efficiency perhaps may lead to innovation being sacrificed for cost reduction. So last June, ENTSO-E published a position paper called Innovation Update through Regulation. You have here how it looks. It was built over the list of the Technopedia solutions of ENTSO-E. This Technopedia is a summary of all possible solutions, innovative and state-of-the-art technologies, cover the fields of transmission assets, of system operations, of digital and flexibility solutions, and all the options that we have seen today are here considered. This position paper proposes a menu of options available to regulators for the adequate support of TSO innovation, depending on the solutions target and the maturity of the existing regulations, and tailored to its TSO situations, because it's true that every country has a different situation. It includes actions such as making more attractive the OPEX-based innovative solutions, having an holistic approach to incentivize innovation for solutions with lower technology readiness levels and their uptake when they achieve sufficient maturity. And once mature, the solutions would require targeted incentives, which could be based on key performance indicators. Well, you can take a look to these position papers and look for additional solutions that are proposed there. Therefore, to conclude, I would like that you take the message that the TUNDP gives a clear view where some solutions is valuable, and it's up to the project promoters with support of the industry, the ones that can define the most appropriate projects with the most beneficial cost-benefit analysis for the society, with the most beneficial CBA. Yeah, in relationship with the TUNDP, the final version of the 2022 release will be published early next year, and you can take a look to the visualization platform and all the information that is in the website to get a lot of variables per country, per border, and to check where there are opportunities around Europe. Thank you.
Thank you very much, Patricia, for that presentation, also for including the Technopedia as current. We are a big fan of the Technopedia, especially showing the technology readiness level, because we say we are the voice of innovative grid technologies, but many solutions are not even innovative anymore. They're already very well established, let's say. So
they are progressing, yes.
Yes. So thank you very much for that. I would suggest that we now open up the floor to all the panelists. I could invite you to turn your camera on. So I guess maybe the first question for Patricia. So do you see the NOVA principle as we have discussed it, just in short, do you see that as one of the main principles in the TYNDP, that you see that this is an approach?
Mm-hmm. Well, as I mentioned, it's taken in the identification of system needs, yeah. But the point is that here it's considered needs and not solutions, yeah. And because here. Talking about the TUNDP, it's the project promoters, the ones that present any projects that has an European relevance, and it's considered by the project promoters, TSO or non-TSO project promoters, that consider that they can solve a need of the system, yeah. And this is open to every type of project. So type of projects that we have seen here can be included. The only restriction is to fulfill the technical criteria mentioned in the guidelines for project inclusion in the T1DP, that mainly it considers the need to increase capacity in a section by more than 500 megawatts and without any limit in the cross-border section. So in the T1DP projects that we have up to now, there are several high temperature conductors, for instance, as they usually provide high capacity increases. Probably in the future, we will see more diverse type of projects. Yeah.
Okay, thank you very much, Patricia. Now, to our other panelists, we've been talking about the NOVA principle, and on paper or on PowerPoint, a lot of these solutions seem like no-brainers. Do you see that this is also being done in practice for how logical it seems? I guess this is a question relevant to all of you. So does anyone volunteer to go first? Otherwise, I will assign somebody.
I could also.
Okay,
mention,
you go ahead,
yeah,
Patricia.
if I can,
Sure,
yeah.
sure.
I'm going to give some numbers of the Spanish case that is the one that I know the most. Yeah, in this national master plan that I mentioned, around 72% of the actions are focused on improving and maximizing the use of existing lines, yeah, minimizing environmental impact. And this is quite relevant because it's true that it's for new right-of-way, it's quite difficult to find new routes, and that is very relevant to try to be innovative and make them the best with the existing infrastructure. Yeah, so in this approach that I've mentioned, for instance, we have more than 7 kilometers, around 23 lines with dynamic light ratings devices, which is quite a lot, and more than 7,000 kilometers of capacity increases. Let's see what type of capacity increases are, and if some of those capacity increases are high temperature conductors or not. Yeah, and only 2,700 of kilometers are new aerial right of way. Yeah, we also have in the plan 2 storage systems as fully integrated network elements in the Balearic submarine links, and they are only prepared for use in case of emergency. So it's something similar. The approach is something similar to the Grid Buster, but it's only focused for the links and it's not in the mainland. But well, it's something quite innovative. And also 5 synchronous conductors in the Canary Islands and in the Balearic Islands as full integrated network elements to allow better integration of RES in the islands and to allow to maximize the capacity of the links as they allow to increase the short circuit power and inertia to the system. So these solutions are ready, yeah. And I think that as in Spain, many TSOs are also counting on them and including them in their plans and in the solutions that they propose to the system needs.
Frederic, thank you, Patricia. Frederic, you have your hand raised. Go ahead, please.
Yeah, I wanted to add to what Patricia just mentioned. I think we're starting to see a mindset change at least with European TSOs and also the American ones. We know Persimmon has a strong presence in North America. It's very recent. I would say it goes back no longer than a year or two. Before that, the mindset of TSOs was very much still to do pilots, to put a toe in the water, test this, test that, test again, test again, and again. We had TSOs who had been testing the same technology for 12 years. That mindset, fortunately, is changing, and that's a good thing. Because this industry just cannot afford that any longer. And I think the energy crisis we're all going for in Europe is acting as a catalyst. And unfortunately, we had to go through that, but it's acting as a welcome catalyst to our industry to deploy those technologies that Patricia just mentioned. And indeed, they are available. They are commercially available. We're not talking about science fiction any longer. And so it's good to see that the mindset is changing. We as an industry, of course, would like to see that mindset change even faster. And to enable that, the regulators have to change also. I think the TSOs have done their share of the job. We're seeing a more innovative mindset coming up. The same change also has to happen at the regulatory side, so that regulators are not afraid to do what it takes to allow those technologies to be deployed.
Thank you, Frederic. A message for regulators as well that we will certainly take to regulators. Lars, you would also like to respond to this.
Yeah, I just want to add to what Frederic said. I think it's absolutely right. I think the mindset with the TSOs, they understand the problem, they know they're good. They understand, they have teams which look at these new technologies and want to integrate them. I think there's the regulator, but what we've also learned is that you also need the government on board, the oversight, even though, of course, regulators per se are independent. But I think government and policymakers also need to be important. For them, it's quite important because grid fees is becoming a bigger and bigger part of cost of electricity. So what we've seen, for example, in Germany, that let's say from the three stakeholders that we need, the TSO, the policymakers, and the regulators, two were on board, and the one other who wasn't too excited got a bit of pressure, I think, and then they went that way as well. But I think when we go this way, I think one issue I have, yes, well, we say we do the NOVA principle, right? But the transparency around it is often difficult to measure. So it is difficult when there are no public information about cost-benefit analysis that is being conducted. It's difficult for us as an industry to understand, have new solutions been considered? Have they been considered correctly? And it's quite intransparent. So in Germany, for the grid boosters, there were like various rounds of calculation of cost-benefit analysis, and the regulator always found a worse business case than the TSOs, which is maybe okay, but it changed between iterations as well. The regulator said, I'm only considering savings over the first 15 years of a 20-year lifetime asset, which is like, okay, you can make that decision. I'm not sure where it's founded and how transparent it is, right? So I think if we can increase more transparency, and I know grid planning is a really intense exercise in Germany, it's a 2-year process, right? We understand that, and there's a lot of consultation in there already. But I think if we can become more transparent about how we plan and do cost-benefit analysis, then we'll get to a better stage that we can more proactively talk about integrating new and smarter technologies in our grids as well.
Yeah, I think we all completely agree on that. That more transparency on how these decisions are made is absolutely needed. And also what you said, that it's done correctly. That the benefits are considered in a correct way. Hey, you wanted to also add to this question.
I did. I've done that classic thing of putting my hand up because I wanted to make about a point about regulation that Frederic then made. And I thought, well, it's okay. I've still got my point about transparency, and then Lars made that point. And it was great to hear from Patricia about the examples from Spain as well. That's really encouraging. I think maybe a few more words on regulation, because I kind of laboured the regulation that exists in the UK and in GB in my presentation for that reason. Essentially, I think the fact that TOs get a share of the benefit if they propose different technologies which reduce costs for consumers. That saving is essentially shared between TOs and consumers. I think has been really important in SmartWires projects going ahead in GB. And if we look across the world, Lars made a point about the time that's needed to pull TO plans together as well, because of their importance. Another area we've been successful in is Australia, where they have sort of different regulatory arrangements for different sizes of projects that can solve more problems more quickly. And you know, that could be something that could be of interest in Europe as well. And the other area where we've been successful is in Latin America, and I think that's essentially because, or largely because, you know, they have competitive arrangements for the provision of transmission in Latin America, and therefore, you know, if your solution is the most cost effective, then you've got a very good chance of winning it. Thanks.
Yeah, thanks a lot for adding that. Even if your previous 2 points were already made, at least we are all on the same page. Peter, you would also like to add something?
Yes, just very briefly. Much of what I wanted to say has been mentioned, and also what Patricia said was very revealing. I mean, just wanted to add a couple of comments. In our experience with TSOs, some always focus on lowest project cost from the perspective of obviously reconductoring and reinforcement from our side. But whereas others we find are more enlightened in their tendering process, for example, when they look at total cost of ownership, you know, so the real lifetime cost. However, that also requires a bit of a dialogue, because we would need to we need to understand the line loadings of the utilities to be able to help them calculate what actually those potential savings would be. The only other thing I would say, based on some other activities we have, I mean, we're finding that the infrastructure finance, the lending organizations outside of Europe are becoming much more enlightened in this area, where they look at the efficiency part of a project as a part of the scorecard, not just lowest project cost. And so that's very encouraging. And many TSOs are adopting that in Europe, but not all.
Thank you, Peter. I think building on that, a question from one of our audience members for Patricia. So I guess whether these incentives, if I understood the question correctly, the incentives, for example, in the ENTSO-E uptake on innovation, has this already been updated at the national level? For example, is that everywhere in place, or is there still a lot of work to do there?
Yeah, I guess that there is a lot of work to do here, and yet it's very different from country to country. Yeah, well, in the case of Spain, we have some standards, yeah, for the conventional solutions, yeah. For the rest is something that is discussed project by project with the regulator. But it's also true that including those projects in the national development plan is something that has been widely discussed with the regulator to ensure that those type of projects were enough mature, and it could be solutions that could be useful. But it's a case by case, and yet we have a path to do to show that they can be included in the conventional toolkit of solutions that we have to solve those needs.
Yeah, thank you. I guess another question from me, how can we also better communicate about the benefits of these technologies, for example, optimization and reinforcement? And as we see that you know, it's really a no-brainer, many of these solutions, and yet we see that it's still not always, it's still sometimes overlooked. So what do you see as an industry that we need to do to communicate better about our solutions? Do I have any volunteers? Okay, Lars, go ahead.
I'll start. Maybe let's say have more current webinars. to educate stakeholders. No, I think I believe understanding where do TSOs and people who do the planning in TSOs talk to each other? Where do they share knowledge and information? Where are those forums where we as an industry can offer our, well, information that we have and provide case studies? And where do we find TSOs actually open to invite us and talking about it? How can we structure market consultations with TSOs, maybe on European level, for them to showcase the technologies that are out there? So I think we need to figure out how can we talk better and more about it, what those solutions can do to the right people within the TSOs. So I think we can push a little, but there will also have to be some pull within the TSOs. And therefore it's great we have Patricia with us today, because she's pulling that knowledge, well, for Spain, and I think we need more of that.
Thank you, Lars. And I guess it's also important for our colleagues in the renewables industry as well to be aware of what is possible. We have one question from the audience, whether there's scope for TSOs around Europe to allow renewable developers that want to connect to constrained circuits to include these innovative solutions as part of their costs and projects for grid connection offers. Do you have any information on that, Patricia, or maybe some of our other panelists? Is this a good idea?
Well, I could say for renewable developers, I could say that all these type of solutions will be more cost effective for the society when included in the transmission grid, in the whole transmission net. So not in the project grid connection offers, to allow the whole system to benefit from them. Yeah.
Okay. Frederic, you would like to add to that?
Yes, we have seen a couple of examples, but not in Europe, of renewable developers actually using, in my case, DLR, and on lines that they didn't even own, that on grid lines, and offering to pay for that investments on behalf of the ESO, just to accelerate the connection of their project. So that we have seen, the odd such example. Again, not in Europe. So maybe that's something that, again, regulators could take a look at. It needs to be looked at with caution, because you don't want to optimize locally at the expense of a lower or higher cost of operating the grid globally. But this is something that potentially could also be considered.
Thank you very much, Frederic. We are almost out of time for today. Does anyone have any last thing that they would like to say, that they came here to say today that they didn't have the chance yet? If that is not the case, then I would like to thank all of our panelists. We heard today about many different grid optimization cases through the smart valve, dynamic line rating, grid boosters, and then Peter representing the V and the A of our NOVA principle, the Verstärkung and Ausbau, the strength, the reinforcement and building new lines. So I guess we can see that there is really a lot that can be done to increase the efficiency of the electricity grid. And we also thank Patricia for presenting her perspective from ENSOE and Red Electrica. So thanks to all of our panelists for today. As we mentioned, the slides will be made available and the recording as well. And thanks to our audience as well for the questions and the Q&A. Always great to have an active audience. And I'm sure all of our speakers will, if you have any further questions, our speakers will be happy to answer them through email. They have provided contact details in their slides. So thank you, everyone. Thanks from Current, and good afternoon.
Thanks a lot. Thanks, everyone.
Thank
Thank
you.
you.
Bye-bye.
Bye.
Everyone. Thank you, Leila. Bye-bye.